All right, so in this video, we're going to be looking at using line integrals in order to calculate area. And so this general formula is the area formula that we can use for line integrals. Now, the difficulty we're going to have is, of course, whatever we're going to find the area of, we need to parameterize it in order to insert it into this formula. So let's look at a couple of examples. We'll start with a circle. So let's say I have a circle of radius 3, x squared plus y squared is equal to 9. And in parametric form, this would be 3 cosine t. Let's put this in, I guess, angle bracket form. Make it easier to type. 3 sine t. And then to get our dr, so our dx and our dy, we would then plug in, take our derivatives, right? So minus 3 sine t and 3 cosine t. And then each of these times dt. And so if we think about the entire circle, right, then our limits of integration for the entire curve would be from 0 to 2 pi. And x is 3 cosine t times dy, which would be 3 cosine t dt. And then minus our y would be 3 sine t times dx would be minus 3 sine t dt. And if we simplify that, we're going to get zero to 2 pi, 9 cosine squared t plus, because it's a minus minus, 9 sine squared t. And we can pull out the common dt, and we can pull out the common 9, and then sine squared plus cosine squared is equal to 1. And what is our integral? Well, 1, the antiderivative is t. We plug in our limits of integration. T becomes 2 pi minus 0. And so we get 9 over 2 times 2 pi, which is 9 pi. Now, this was a circle of radius 3. So think about our formula, pi r squared. Well, that would be pi times 3 squared, which would be 9 pi. So we get exactly the same answer that we would get from the general geometry formula for a circle. Great. So let's think about this from the standpoint of a parabola. Now, the area under a parabola, we would have to calculate manually, right? So we would have to use regular calculus to find the area of it. So let's do this sort of the traditional way. let's say find the area under the parabola. Let's make it nice and simple. X squared between 0, x equals 0, and x equals 2. So standard area procedure, just so that we have a value to compare it to. We would integrate from 0 to 2, area under the parabola. We would get x cubed over 3, and then we would evaluate that from 0 to 2, and so we would get 8 over 3. Okay, so now we have our basis for comparison. So now let's think about, in order to use the area formula we noted above, we would need to parameterize our path. Now, for a parabola, we're going to have a little bit more difficult time, because if we're thinking about the area under the parabola, draw a little sketch here. Here's our parabola. We're evaluating the area under here, right? So if I want to create a path around the parabola, yes, I'll have this segment of the path, but then I also need this segment of the path, and I need this segment of the path. And normally you do them clockwise. Either way is fine. But you need to do those parameterizations, and for this problem, we're going to need to create 3 paths. So let's think about, this is the point 0, 2. So we're going to go on a straight line on the path from 0, 0 to 0, 2. So in the space of, let's say, 1 unit, we're going to go 2t, and y stays 0. And then r2 of t, we're going to go from the point 2, 0 to the point 2, 4, because that's the point where the parabola intersects, right? So now x stays 2, but now we go straight up, so that goes for t, again, on the interval 0 to 1. We don't need to really keep changing the value of t. We can if we want to, but it just makes the math harder. And now we need to come back down the parabola from x equals 2 to x equals 0. So we want x to be negative, and we want the path to be x squared. So again, you can think of this as t, negative t. Actually, that's not quite going to work. You're coming from starting at 2 and then coming back down. Yeah, that's better. You're coming back down to t. So there's a path of -1. This one will be on the interval 0 to 2. Yeah, so let's label these just so that we're remembering. So this one will be on 0 to 2. And then if this is my parameter, let me just double check the values. I want to start when t is, nope, I'm going to have to do 2 minus t. So when t is 0, I'm going to start at 4. And then when t is 2, I'm going to end up at 0, 0. Okay, so that's better. That makes me happier. Always plug in points to kind of double check to make sure that the math is working. one possible thing that you can do is you can just parameterize this going from 0 to 2, sort of in the standard way. And and then what you would do is you would just flip the sign because the orientation is backwards. And so that also works okay. But when we're doing this sort of formally, sometimes it's better to be sort of more careful. But I will just say alternatively, integrate. This would be going the traditional 0 to 2 way on T. Yeah, the math will be easier if you do this. 0, 2, but then flip the sign since the orientation is reversed. So in our diagram, what we need to do is we need to go counterclockwise. It's the standard orientation. If you go clockwise, the lines are a little easier to make negative. But what you end up doing is that you get the negative of the area. So the sequence that you go around is important. I'm going to integrate this one, and then we'll think about the sign that we get when we do that, because we want to be able to add these up in order to get that 8 pi over 3. But I'm all about, making the algebra less nasty. Integrating this will be a headache. So let's think about our dRs that we're going to need for our dy and dx. So this will be 2, 0 for the first one, 2t and 0, and then dr2, that's going to be 0 and 4 dt, and then d3. Again, I'm going to use the simpler version, but I need to keep track of that sign. dt and 2t dt. Now my 3 integrals then, let's do area is equal to 1/2. And I'm going to put my brackets around all 3 of my integrals. 0 to 1. Now my x for my first one is 2t, dy is 0. And then, again, let's go back and look at our x dy, and then y dx. Dx is 2 dt. That's 0. So then plus, here's my integral, 0 to 1. Now on this one, x is 2 and dy is 4 dt, minus y is 4t, but dx is 0. And then I'll do this plus minus because we want to check the sign because of our orientation. 0 to 2, and x, again, I'll using the simpler one, x is t, and then 2t dt is dy, minus t squared, and then dt is our dx. Now, as I said, this first thing, this is all 0. So it's gone. This one, this second component is 0. So let's just write the simplified version. 0 to 1, 8 dt. And then again, we'll check the signs here. And this will be 0 to 2. This is 2t squared minus t squared dt, which is going to give me just regular t squared. So we'll copy all of this. Now the limits are different, so we can't combine the integrals. We just have to integrate each one separately. If I integrate 8, I get 8t, and then I plug in my limits, I get 8, and then we'll check the signs here. This one is going to become t cubed over 3, and I'm going to plug in my, just on this term, my 0 and 2. And so I'm going to end up with 8 plus, now the 0 doesn't do anything, plus or minus 8/3. Now, which sign am I going to use? Well, I'm thinking I'm going to use the minus sign. So because of the orientation. So let's double check if that's appropriate. What is 8 minus 8/3? Well, it's 16/3. And half of that is 8/3. And that does agree with our previous expectation from just regular calculus. So I'm going to go back and I'm going to put in just the minus signs. Again, sometimes it's a good idea just to kind of keep your sort of mental pathways open to the possibility. But that it's that orientation issue that makes the negative sign necessary for this final integral. Again, if we had integrated the original parameterization, that 2 minus t and the 2 minus t squared, we would be fine. But there would just be a lot more arithmetic we would have to do in order to get to this answer. But that was the orientation that we would need, the expression we would need if we were starting at t equals 2 or x equals 2 and going backwards to x equals 0. But if we go in the standard orientation for a parabola in the positive direction, the reverse orientation, it just flips the sign. Now, why, you might wonder, like, this was an awful lot more work than just doing it by the regular way. Why are we doing this? Well, not every function is going to be this messy. Parabolas are better suited to finding the area under the curve in standard regular Calc 1 way, not this way, not the Calc 3 way, not with line integrals. But the circle formula wasn't actually that bad. So it depends on the curve. It depends on the kind of function that you're dealing with. Sometimes this will be relatively straightforward. We didn't even have to do any integration really for, we were just integrating 1 for the circle example, and we got the right answer. So sometimes if we're dealing with complicated polar curves or things like that, this can be a nice way to do that integration that we might not be able to do with the standard old-fashioned Calc 1 way. It's nice to know that if we have a sort of old-fashioned standard, parabola graph, that we can get the same answer, that it does extend beyond just the polar case or other kinds of parameterization cases. But You want to, usually you want to choose the process that is the simplest and not the process, not choose a process that is overly complicated for that particular scenario. So we did this as an example just to show that yes, it does work. But that's not to say that if you're confronted with a problem, find the area under a parabola, that this is an ideal way to do it.